Okay, so finally, let's take this one step further and look at learning from meshes and graphs. Okay, so meshes and graphs are regularly connected and or highly curved domains, and they are vital for many biomedical workflows, including investigation of patient or protein interaction networks, models of molecules, models of human brain networks. Meshes are vital for statistical shape models and physics-based simulation. And the challenge when working with meshes and graphs is that they cannot be described by a Euclidean coordinate system, which makes them much less convenient to design efficient learning operations. So Euclidean domains are defined by data that lives on a regular flat grid where the distance between points is always the same, and this makes it super easy to define a regularly shaped convolutional kernel that always fits perfectly over the input data grid. So it's perfect, exactly the same shape of elements because the distance between these points always the same. And the other thing that's really convenient about Euclidean domain is that they're defined by a global coordinate system which determines exactly how we are to transform this filter over the domain, i.e. by translation, in order for us to spatially implement that convolutional filtering operation. And all this can be made extremely efficient to implement on GPUs through matrix multiplications, because we can just unwrap our regularly shaped filter and we can unwrap our regularly shaped image patches, and we can just multiply them together such that this matrix multiplication operation exactly corresponds to the spatial convolutional filtering operation. From this, we then get this added bonus that the convolutional operation is equivariant to translations, meaning that we get the exact same result if we convolve and then transform, or as if we had transformed and then convolved. So remember that I've said many times that the output of a convolutional operation is an image, and if you can see from this image, this video, then the activation map returned from the convolution as it's moving over the view looks exactly the same. It just translates in exactly the same way. So this is why CNNs are transformation invariant. It doesn't matter where an object is in a scene, it will look the same in the activation map, so it can be detected or segmented wherever it is. And none of these things are true for regularly tessellated surface meshes or graphs. Filters cannot be defined as having a uniform shape, because our mesh or graph will be irregularly tessellated with different distances between our vertices, and each vertex will have a different number of neighbours. We also can't transform our filters over a surface in a uniform way because there is no global coordinate system. Coordinates are instead local and defined relative to a tangent plane. So two different paths. If you transform a filter over even a sphere in two different directions, the orientation of that filter at different locations will be completely different. One way of adapting the concept of convolutions to irregular tessellations is to have filters that are invariant to the ordering of vertices and can adapt to nodes with any number of neighbours. And the most popular way of doing this currently is through message passing learning frameworks such as graph attention networks. The idea here is that the update to each node's hidden state, H, is calculated by aggregating over messages that are sent from all of its neighbours. These neighbours' weights, these EBA, could be weighted equally, but graph attention networks weight these adaptively based on what they consider the relative importance of each neighbour, where that importance could be informed by geometric priors like geodesic distances between the nodes on the surface of graph. Indeed, an even more simple spiral convolution approach was recently used by Konrad Wagstahl's lab in order to detect very subtle epileptogenic brain lesions from structural MRI. These lesions are very, very subtle and difficult to spot and can often be missed by non-specialist clinicians. and yet these surface convolutional methods performed exceptionally well. However, in my opinion, transformers translate in an even more direct way. All we need is a way of patching our domain, which for brain surfaces we can do by projecting the surfaces to spheres, because brain hemispheres are conformally equivalent to spheres, and spheres have these approximately regular triangular icospheric tessellations associated with them. So we can extract these triangular patches this time instead of squares, linearly embed them, add positional embeddings, and pass them through the exact same transform architecture as we would use for a vision or language transformer. So in this sense, transformers and other similar sequence modelling approaches such as Mamba could arguably be described as more flexible and powerful than surface CNNs, particularly considering their added capacity for modelling these long-range dependencies, which are particularly useful for brain encoding tasks. So in this example shown here by my former PhD student Simon Danhorn, this was initially benchmarked on the task of brain age regression from neonatal cortical MRI data. So the idea was that we needed to predict how old a baby was from their cortical morphology, benchmarked it against surface CNN approaches. So this is spherical UNet, this is the MONET, and what you find in these early results is that surface transformers significantly outperform them, particularly for cases where we haven't previously run image registration to optimally align the shape of, or overlap the shape of individuals' cortical morphology. So our surface convolutions are either not very transformation equivariant and only work when our data is overlapping, or these early surface convolutional approaches weren't learning such powerful or expressive convolutional filters. And then once we've made this conceptual leap to translate the vision transformer to another domain, then we can begin to translate all the other major architectures used to improve training of VITs, including generating surface swim transformers that support dense prediction tasks such as segmentation. So the only difference here really being that the patches are triangles, not squares. I would note here that the icospheric tessellations are particularly handy because they can be regularly upsampled and downsampled. So here this big yellow triangle comes from a relatively low resolution icosphere, and then the yellow and white grids depict all triangular faces of a higher resolution icosphere, all the faces that fit within that larger yellow patch. We can also create surface masked autoencoders using the exact same architecture and training framework as the original masked autoencoders. And here we're seeing how these are used to reconstruct the complex patterns of dynamic brain activity from functional MRI, even when 75% of the patches are masked out. So you can see that the data that goes into the masked autoencoder, you can hardly see any structure whatsoever, whereas what comes out is something that much more closely resembles the input, with the yellow here representing areas of the brain that are connected and talking to each other. And that needs to be inferred just from these few remaining patches of yellow that you can see that go into the encoder. And then when you put all of these things together, you can start to use these systems to decode what an individual is watching in an fMRI scanner, even for unseen subjects, which you have absolutely no idea what this brain topography should be, so where the brain areas are as indicated by the yellow regions that are firing up. For example, you can encode brain activity using a video surface masked autoencoder. You can encode some movie clips that the individual is watching in the scanner using a video transformer. You can encode the audio with an audio transformer. These are all transformers, and then you can align them with clip contrastive learning, where clip-based learning basically works to push together or make more similar the embeddings of brain activity and videos and audio when those embeddings are taken from the same period of time where the individual is watching some specific movie, and you're looking at the embedding from that part of the movie, then their brain activity and the movie should align. But if you jumble this up and you give the embedding from the brain activity from some part of another movie and you give it a different movie, then the embeddings from those two should be different, and therefore they're pushed apart. And then if you use this joint training framework, you can then use it to predict what an individual is working in the scanner, because if you know what their movie embedding should be, then you should know what their brain activity embedding should be. And if you take it even further, you can start to generate scenes of movies just from patterns of brain activity. And this is all done with vision transformers. And I would say that a lot of the foundational models that are now being used to perform general tasks are based on transformers rather than CNNs. Similar ideas have been applied to shape modelling, for example, in this mesh window-based transformer paper. They again patch the image into triangles, explain each patch with features that capture the topology and geometry of the mesh, and then model these tokens with a transformer to perform shape classification and segmentation. People have also used transformers to model dynamic graphs, first using graph convolutions to encode a latent representation of a brain network extracted from the correlation of time series that captures brain activity within fixed regions over a period of time. Then transformers were used to model the temporal evolution of these windowed networks over time. So in summary, transformers are powerful and flexible learning frameworks that can be applied to a broad variety of domains, including non-Euclidean ones. In this space, we still suffer from the problems of high complexity and high numbers of parameters. However, many of the solutions already proposed for vision transformers can be translated to these domains.